Welcome to the new era of video creation with Bayozi. This is our new series on teaching deep learning. Today we will discuss the convolutional neural networks. Here are the contents. Convolutional neural networks, CNNs, are a specialized class of deep neural networks that are primarily used for processing structured grid data, such as images. The key difference between CNNs and traditional fully connected networks is the architecture. CNNs consist of layers that apply convolutions, making them highly effective for image-related tasks. CNNs leverage the spatial relationships in images by using filters or kernels to detect local patterns like edges, textures, and shapes. This characteristic makes CNNs ideal for computer vision tasks such as image classification, object detection, and segmentation. CNNs are also widely used in fields beyond image processing, including natural language processing, NLP, and even time series analysis. In this lecture, we'll dive into the structure of CNNs and explore how they are able to extract meaningful features from raw image data, providing better performance than traditional neural networks for visual recognition tasks. A typical CNN architecture consists of several different types of layers: convolutional layers, pooling layers, and fully connected layers. The first part of the CNN architecture is the convolutional layer, where the network learns to apply filters, also called kernels, to input images to detect patterns such as edges, textures, or even complex shapes. These filters move across the image, performing a convolution operation to generate feature maps. After convolution, pooling layers, typically max pooling, reduce the spatial dimensions of the feature maps, summarizing the information and making the network invariant to small translations of the input. Finally, fully connected layers are similar to traditional neural networks and are used to make the final classification or prediction. These layers receive the high-level features extracted by the convolutional and pooling layers and perform the final decision-making. By learning a hierarchy of features, starting from low-level patterns to high-level object representations, CNNs are able to efficiently recognize complex visual patterns. The convolutional layer is the core component of a CNN. In this layer, the network applies filters, or kernels, over the input image. These filters are small matrices, such as 3pq3 or 555, that move across the image with a certain stride, the step size at which the filter is applied. The filter performs a dot product between the filter values and the image pixels it overlaps, producing a single output value. As the filter moves across the entire image, it generates a new feature map. Filters are learned during the training process, meaning that the network automatically adjusts the filter weights to capture relevant features. The first layer of a CNN typically learns low-level features like edges and corners, and as you go deeper into the network, filters capture increasingly complex patterns, such as textures, shapes, and finally, high-level object features. The filter size and stride play an important role. Smaller filters, like 3keg3, capture finer details, while larger filters capture more global features. The stride determines how much the filter moves during the convolution, with larger strides reducing the spatial dimensions of the output. Activation functions play an important role in CNNs, just like in traditional neural networks. After the convolution operation, the output is passed through an activation function to introduce nonlinearity into the model. Without nonlinear activation functions, CNNs would only be able to model linear relationships between inputs and outputs, which limits their ability to learn complex patterns. The most common activation function used in CNNs is ReLU, rectified linear unit, which replaces all negative values in the output with 0 and leaves positive values unchanged. ReLU is computationally efficient and helps address the vanishing gradient problem, which can slow down or halt learning in deeper networks. Other activation functions like leaky ReLU or ELU, exponential linear unit, can also be used in some cases to overcome ReLU's limitations, such as when neurons become inactive due to the dying ReLU problem. Activation functions allow CNNs to learn nonlinear decision boundaries, making them suitable for solving complex visual tasks like image classification. After the convolutional layers, CNNs typically include pooling layers, The main purpose of pooling is to reduce the spatial dimensions of the feature maps while retaining the most important information. This helps reduce computational complexity and prevents overfitting. Max pooling is the most commonly used type of pooling, where a filter is applied to a local region of the feature map, and only the maximum value is retained. This operation helps capture the most important feature in each region while discarding less important information. Another type of pooling is average pooling, which computes the average of values in a region. Pooling layers also make the network more invariant to small translations and distortions in the input, meaning that slight changes in the position of objects in an image won't significantly affect the output. This property is important for generalizing the model to new, unseen data. Pooling helps keep the model computationally efficient by reducing the size of the input to the next layer. After the convolutional and pooling layers, fully connected layers are used to make predictions. These layers are similar to those found in traditional neural networks, where each neuron is connected to every neuron in the previous layer. The purpose of fully connected layers is to take the high-level features extracted by the convolutional and pooling layers and convert them into a final prediction or classification. For example, in an image classification task, the fully connected layer would take the features corresponding to the presence of various shapes, textures, and patterns, and combine them to predict the class label of the image, e.g., cat or dog. The fully connected layers are typically used towards the end of the CNN architecture, where the high-level information is already available from the previous layers. The network adjusts the weights of these connections during training to minimize the classification error. When applying filters in the convolutional layers, two important concepts come into play: stride and padding. Stride determines how far the filter moves across the image with each step. A larger stride results in a smaller output dimension, as the filter skips over more pixels. Conversely, a smaller stride generates a larger output, as the filter moves more slowly. Padding involves adding extra pixels, usually zeros, around the border of the image before applying the convolutional operation. Padding helps control the spatial dimensions of the output feature map, ensuring that important information near the edges of the image is not lost. There are two main types of padding: valid padding, which applies no padding and reduces the size of the image, and same padding, which adds enough padding to keep the output size the same as the input size. The choice of stride and padding affects the spatial dimensions of the output feature maps and is an important consideration when designing CNN architectures. The receptive field of a neuron in a CNN refers to the region of the input image that influences the neuron's output. In the early layers of a CNN, neurons have a small receptive field that allows them to capture local features, such as edges or corners. As the network gets deeper, the receptive field of neurons becomes larger, allowing them to capture more global patterns, such as textures, shapes, or even entire objects. This hierarchical learning process is one of the strengths of CNNs, as they can learn to detect simple features in the first layers and more complex features in the deeper layers. The receptive field increases as more convolutional and pooling layers are stacked, which allows the network to learn broader patterns and dependencies in the data. The idea of the receptive field is crucial in understanding how CNNs process and interpret spatial hierarchies in images. The training process of a CNN follows the same general principles as other neural networks, consisting of a forward pass and a backward pass. During the forward pass, the input image is passed through the network, with each layer performing a specific operation, convolution, activation, pooling, to extract increasingly complex features. Finally, the fully connected layers generate the network's prediction. After the forward pass, the loss function measures the difference between the predicted output and the true label, quantifying the network's prediction error. During the backpropagation step, this error is propagated backward through the network, and the weights of the filters and fully connected layers are adjusted to minimize the error. Optimization algorithms such as gradient descent and its variants, e.g., ADAM and RMS prop, are used to update the weights based on the gradients of the loss function with respect to the weights. CNNs have proven to be highly effective in a wide range of applications, primarily in image-related tasks. One of the most common applications is image classification, where the goal is to classify an image into one of several predefined categories, e.g., identifying whether an image contains a cat or dog. Another important application is object detection, where CNNs not only classify objects in an image, but also identify their location within the image by drawing bounding boxes around the detected objects. Image segmentation is another area where CNNs are used, where each pixel in an image is classified into a category, allowing the network to delineate different regions or objects in the image. Beyond image processing, CNNs have also found applications in facial recognition, medical imaging, e.g., detecting tumors in radiology images, and even natural language processing, for tasks like sentiment analysis and machine translation. To summarize, convolutional neural networks, CNNs, are a powerful and specialized type of neural network designed to process grid-like data, such as images. CNNs leverage key operations such as convolution, pooling, and fully connected layers to automatically learn hierarchical features from raw data, making them extremely effective for visual recognition tasks. The structure of CNNs allows them to detect both low-level patterns, like edges, and high-level object features, which is essential for tasks such as image classification, object detection, and segmentation. With their wide range of applications in fields like computer vision, medical imaging, and even autonomous vehicles, CNNs continue to drive the advancements in deep learning. Understanding the core principles behind CNNs is essential for developing cutting-edge models in these domains. And as deep learning research progresses, we will likely see even more innovations and improvements in CNN architectures.